Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for MTech EC first semester students. Myself, Dr. Surojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. Today, we are going to start a new module that is baseband signal receiver and probabilities of bit error. And the topic for today's discussion are peak signal to RMS noise output ratio and probability of error. And the lesson objective of the today's topic is analyze various baseband receivers and compute their probabilities of bit error performance and compare their performances. And this topic is mapped with CO number 5. So let us start lecture number 1 from the module of baseband signal receiver and probability of error. So a data transmission system using binary encoding transmits a sequence of binary digits, that is ones and zeros. These digits may be represented in a number of ways. For example, 1 may be represented by a voltage plus V held for a time t 0 to t, and 0 is represented by a voltage say minus V hold for an equal time. In general, the binary digits are encoded so that 1 is represented by a signal S1t and 0 is represented by a signal S2t. Each have a duration of t second. Now the resulting signal may be transmitted directly or used to modulate with a carrier. The received signal is corrupted by noise, and hence there is a finite probability that the receiver will make an error in determining within each bit interval whether a 1 or a 0 was transmitted. So in this section, we make calculations of such error probabilities and discuss methods to minimize them. First is the baseband signal receiver. Consider that a binary encoded signal consists of a time sequence of voltage levels plus V or minus V. In the last slide, so a binary sequence consists of a large number of plus V, that is ones and zeros, which is transmitted from a sender through a channel. Now we are interested only in knowing within each bit interval whether the transmitted voltage was plus V or minus V. With noise present, the receive signal and noise together, this is the receive signal plus noise, together will yield sample values, and generally it differ from plus V or minus V. Now suppose that the noise is Gaussian and the noise voltage has a probability density which is entirely symmetrical with respect to 0 volt. Then the probability that noise has increased the sample value is same as the probability that noise has decreased the sample value. Now, if the sample value is positive, then the transmitted voltage level was plus V. And if the sample value is negative, then the transmitted voltage level was minus V. So that was the decision or decision rule. Again, I am repeating. If the sample value is positive, then the transmitted voltage is interpreted as say plus V. And if the sample value is negative, then we interpret the transmitted voltage as say minus V. Then there is no question of errors. Then when there must be an error, when an error occur, now it is of course possible that at the sampling time, the noise may be of magnitude larger than V, and has the noise may be of magnitude larger than V and has the opposite polarity. So suppose that, again I am repeating this important point. So suppose at the sampling time, noise may be of magnitude larger than V and has the opposite polarity. Then according to, based on the terminology, we are assuming, we interpret, we concluded that minus V, because it is a negative, so it is interpreted minus V was transmitted. Now in this case, an error will be made. Here, the transmitted, in this figure, the transmitted bit is represented by the voltage plus V, which is sustained over an interval capital T, say T1 to T2. Now noise has been superimposed on the label plus V, so that voltage V represents the received signal and noise. Now if now the sampling should happen to take place at a time say T equal to T1 plus delta T, an error will have been made. Okay. So suppose this is a baseband signal receiver. Here the input signal is T with added white Gaussian noise in T of power spectral density GNF equal to eta by 2 is presented to an integrator circuit. This is called an integrator circuit using op-amp. Now at time t equal to 0 plus, we require that the capacitor C be uncharged. Such a discharge condition may be ensured by a brief closing of switch SW1 at t equal to 0 minus. thus relieving C of any charge it may have acquired during the previous interval. The sample is taken at the output of the integrator by closing the sampling switch SW2. The sample is taken at the end of the bit interval at t equal to say capital T. The signal processing indicated in this figure is described, it is called integrate and dump. The term dump referring to the abrupt discharge of the capacitor after each sampling by dump switch SW1. So this is the description how this circuit operates. Now we are going to calculate peak signal to RMS noise output voltage ratio. So peak signal to RMS noise output voltage ratio. The integrator yields an output which is the integral of its input multiplied by 1 by RC, or it is called tau. Then we have the output of the integrator, say V0t equal to 1 by tau integration 0 to t st plus nt dt. So 1 by tau integration 0 to t st dt plus 1 by tau integration 0 to t nt dt. Now the sample voltage due to signal S0t equal to this term, that is 1 by tau 0 to t st means plus v into dt, that is vt by tau. Now the sample voltage due to noise, which is represented as N0t equal to 1 by tau 0 to t integration of 0 to t nt dt. Now the noise sampling voltage N0t is a Gaussian random variable in contrast with NT, which is a Gaussian random process. The variance of N0t is say sigma 0 square, which is the mean square term of N0t, that is N0 square t bar, which is eta t by 2 tau square, where eta is the RMS noise power. So the output of the integrator before sampling, the switch is V0t equal to S0t plus N0t. The signal output S0t is a ramp in each bit interval of duration capital T. At the end of the bit interval, the ramp attains voltage S0t, which is plus Vt by tau to minus Vt by tau, depending on whether the bit is a 1 or a 0. Therefore, S0t equal to the signal output of the integrator. This is the signal output of the integrator, where S0t belongs to plus Vt by tau to minus Vt by tau. Now at the end of each bit interval, the switch SW1 closes momentarily to discharge the capacitor so that S0T drops to 0. The sampling switch SWT closes briefly just before the closing of switch SW1 and hence read the voltage, that is V0T equal to S0 capital T plus N0 capital T. Hence, the signal to noise ratio S0T square by N0T square bar equal to, just put the value of signal power from the previous slide, that is this square V square T square by tau square, and this is eta variance eta 0 square, that is eta T by 2 tau square. So if we put here, ultimately we get 2 by eta into V square T. The signal to noise ratio increases with increasing bit interval T, and it depends on V square T, which is the normalized energy of the bit signal. Therefore, a bit represented by a narrow high amplitude signal and one by a wide low amplitude signal are equally effective, provided V square T is kept constant, which is nothing but your normalized energy. Then probability of error calculation for integrate and dump filter. The function of a receiver of a data transmission is to distinguish the bit 1 from the bit 0. In presence of noise, we now calculate the probability of error PE for the integrate and dump receiver. We have seen the probability density of the noise sample N0T is Gaussian. Then its density is therefore F N0T equal to e to the power minus N0 square T by 2 sigma 0 square by square root of 2 pi sigma 0 square. So this is the PDF or probability density function. Sigma 0 square is the variance, which is N0 square T by bar. Now suppose that during some bit interval, the input signal voltage is held at say minus V. Then at the sampling time, the signal voltage is S0T equal to minus Vt by tau, while the noise sample is N0T. Now, when does the error occur? Now, if N0T is positive and larger in magnitude greater than Vt by tau, the total sample voltage V0T equal to S0T plus N0T will be positive. Such a positive sample voltage will result an error, and say the error probability of error is say in PE, which is say the limit of the integration is say plus in this part the error is occurred. So this limit should be Vt by tau to infinity. And the PDF f n0t dn0t. Then Vt by tau to infinity and f n0t is already shown here. That is the PDF of a Gaussian noise, Gaussian distribution. So e to the power minus n0 square t by 2 sigma 0 square by square root of 2 pi sigma 0 square and dn0t. Now how to solve this problem? Define x equal to n0 t by square root of 2 sigma 0. Therefore, probability of error equal to half into 2 by pi square root of x equal to v into square root of t by eta into infinity e to the power minus x squared dx. So this is half ERFC v into root over t by eta. That is half ERFC v square t by eta to the power half. So probability of error equal to half into ERFC ES by eta to the power half, where ES equal to signal energy of a bit, which is V square into T. So ERFC is the complementary error function. That is, if this argument is high, then its complement error probability will be less. Okay. So if we draw a curve, that is probability of error versus ES by eta according to this expression, then this curve is monotonically decreasing and it has an amplitude of, now suppose this is 0, this term is 0, then error probability will be 1. So sorry, it should be half. This argument part is 0, then ERFC of 0, that is 1, and it is multiplied by half. So probability of error is half. It starts from half, that is 0.5. Now, what is the significance of this curve? It is monotonically decreasing with ES by eta in dB, say. Note that probability of error decreases rapidly as ES by eta increases, and the maximum value of PE is half. Thus, even the signal is entirely lost in the noise, so that any determination of the receiver is a sheer guess, and the receiver cannot be wrong more than half the time on the average. So that means even the signal is entirely lost by the noise, the receiver prediction cannot be wrong more than half of the time on the average. Okay. So this is all about your baseband receiver and probability of error calculation of integrator and dump filter or dump receiver. So let us stop here. Thank you. And in the next class, we discuss on optimum filter. Okay. Thank you.